Hello, my name is Harry Crocker, and I'll be going through my Lab 5 for Physics 2 on magnetic braking with Faraday's Law. The purpose of this lab was to observe and model Faraday's Law acting on a falling magnet, and in the sections of this lab I'll be going through the introduction, experiments and results, computational model, and then finally a discussion. Some of the fundamental principles that were applied in this lab are the Biot-Savart law, Faraday /Lenz's law, Newton's second law, which is F equals ma, and Ohm's law, which is voltage equals current times resistance. Some of the other fundamental principles used were the magnetic dipole moment and the magnetic force, as shown in those two equations there. As for the experimental data, the length of the aluminum foil was 0.3 meters, width 0.005, inner radius was 0.025, outer radius was 0.03, resistivity was 2.65 to the power of -8, and for the bar magnet, the mass and mu are listed there. For part 1 of the procedure, locating the magnetometer was the first part, which mark the north pole of the magnet, hold the tube vertically, and position the tube in the frame of the phone camera. Then the magnet was dropped, and over 5 trials, an average time of 1.243 seconds was recorded. For some checkpoint questions, why can't we use a ferrous tube? Ferrous means that the main component of the material is iron, which would skew the results compared to aluminum. And what happens to the magnet? How does this compare to a magnet falling in free space? In free space, it falls much faster than it did through the aluminum tube because of the induced magnetic fields. Now on to the first part of the computational model. So a plot of velocity versus time set up there at the top, and then the geometry of the tube is established with length, width, inner radius, and then radius, and then the numerical parameters of the simulation are dialed in there from lines 40 to 47. And next, creating the tube of aluminum foil as a series of rings stacked along the y-axis. The y-axis is perpendicular to the plane of each ring and passes through the center of each ring, as you can see there in the for loop. Then in the next part, the properties of the magnet were laid out, and the visualization of the bar magnet as well. Next, the initial conditions are dialed in for start times, and then a function was written to calculate the magnetic field of the bar magnet, and then this next function was added to calculate the magnetic flux. In a section of code here on line 147, it calculates the gravitational force on the magnet, and then the gravitational force, the magnetic force of the tube on the magnet is calculated there. Then the current in the ring is calculated, and that is induced current. And then the ring is colored according to how that's set up, which will be shown in a later slide. And then the magnetic force on the magnet is calculated, as well as the magnet's velocity and position. And then that is all plotted on a graph as seen on this next slide here. Here are the results from the simulation. You can see at the top is the visualization, as I mentioned earlier, and then the velocity versus time curve on the left was plotted using a magnetic dipole moment of 5.5, and the one on the right was plotted using a magnetic dipole moment of 2.136. For the questions here, blue indicates counterclockwise. Dynamics of the system are all inverted, and the computational model was much slower than the real world system, which could be due to difference in thicknesses of aluminum foil. And then a steeper velocity versus time plot just tells you that there's a stronger force acting on the bar magnet. What if the resistivity of the conductor were reduced as close as possible to zero? So this would cause, as that gets lower, then the magnet will take longer to fall. And what if holes or slots were cut into the tube? This would interfere with the induced current, which would mess up the magnetic forces causing the magnet to fall faster.